Okay, so uh, now GPUs have different types of memory. Okay, each memory is good for a specific purpose. So, like for example, we have this constant and texture memory. I will not discuss about it. We will mostly discuss about local, shared, and global memory. So this is increasing visibility of data between threads. So local memory is local to that particular threads, but to that particular thread. Shared memory is visible to all the threads in a block, and global memory is visible to all the threads on the GPU. So this is the hierarchy. Okay. If you know about cache hierarchy, then it is fine. If you do not know, I hope you would have seen my lectures on cache memory and cache hierarchy. Lecture number 4A, 4B, and 4C. So here we have this L1 cache to L2 cache to DRAM, and parallel to L1 cache is the shared memory. So although it's called memory, it is not on the DRAM, it is on chip. The shared memory access is very, very fast, just like L1 cache because it is on chip. Okay, so remember L1 cache is hardware managed. Okay, and shared memory is software managed. Okay, so I will later on discuss many accelerators. Many of them will have software managed cache. So CPUs usually have hardware managed cache, right? CPUs traditionally have hardware managed cache, but most of the accelerators we'll see, nearly all of them, they will have software managed cache. So what is the difference between hardware managed cache and software managed cache? Okay, just let me close the door. Okay, so what is a software managed cache? So, see, if a programmer can write a code to move the data to this cache, that's called software managed cache. Whereas, if if the management of the cache is entirely in the hardware, that means you cannot write any code to move a data to L1 cache or L2 cache. The hardware will do it automatically. For example, you must have written Python code or C++ code which runs on the CPU. Right? Now CPU has L1 cache, L2 cache, and so on. But you never wrote your code to move a particular data to L1 or L2 cache. Hardware will make its own decision. Which data should be moved into L1 cache, L2 cache? That is hardware's decision. It is not programmer's botheration. Programmer does not have to think about it. Okay, so that's the idea. So if programmer does not write any code to move the data to a particular level of cache, that is called hardware managed cache. Whereas software managed cache is that cache where the programmer can write the code to move data to that cache or memory. So that is called, yes, shared memory is actually a cache. It's a software managed cache. Okay. So here, as I said, we have local, shared, and global. So here we have uh, local memory, which is private to each thread. Then we have a thread block, which has many, many threads, and all the threads in this block can share the shared memory. Okay, and we have multiple grids, and all the threads in those can access the global memory. Okay, so CUDA hierarchy of threads, blocks, and grid with corresponding per thread private, per block shared, and per application global memory spaces. So if you remember these diagrams, you can very easily visualize what's all happening. So now let us discuss first local memory, then shared memory, then global memory. So each thread has its own local memory. So location at address 100 for thread 0 is different from location at address 100 for thread. So it contains local variables which are private to each thread. Now there is global memory. Actually, we have not discussed CUDA, so you may not understand this, so you can ignore it. So each thread in the different thread blocks can access the same global memory. So here, when you say access the address 42 from global memory, then whether you access it from this thread or any thread, they will access the same data. Whereas here, this 42 is different from the 42 of this thread or this thread or this thread, they will all have different data to be accessed from a particular location. So global memory access is slow, right? Because global memory is in DRAM. And in fact, one more thing is actually I should have written it here, but local memory is also in the DRAM. Okay, so DRAM has both local memory and global memory. They are both in DRAM. But who can access this? That is different. Suppose you take the example of library. Now, library has almost all the books which anybody can issue. It's not that they are reserved for me. Anybody can issue them. Okay. So, but suppose some director, right? He has some special books which are reserved only for him. They are his books. Nobody else can issue them. But they are not kept in his office. They are kept in the library. So although those books belong to the director, but those books are not kept physically close to him. They are kept in the library. Okay. So is it fine? So local memory or access is also, because it is the DRAM, that is also slow. So here also I should have added the word slow access. I will actually add it. So this is access is slow, but and global memory access is also slow. Now comes shared memory. So shared memory is access is fast because this is all on chip. This is on chip. So shared memory is also on chip. So this access is fast. Now shared memory, each thread in the same block. So here each thread in the same block, they can access a memory region called shared memory. It is limited size, tens of kilobyte. And it is used as a software managed cache. So I already explained what is software managed cache. That means the programmer can write a code to bring the data to the cache. And as I said, the programmer can write the code. So there are some synchronizations that also is required. So synchronize threads in a thread block using sync threads. So I will explain why I think sync threads is required. So if you have any questions till this point, please ask. No questions? So how come there are only, I think there are only 16 participants, usually that is more than 20. Is it that, can somebody log into the Teams and see if somebody is waiting there? So Prashant or Anubha, can you please do it? So Sagar is not here.
Yes, sir.
Please log into the Teams and please tell them that the class is happening today on WebEx. Actually, I could not log in. I will try to resolve that issue. Okay, so now let us try to understand this analogy, which will explain to us how shared memory works. So, suppose I have one student of EC department, another student of EC department. If they go to the institute library for all the book requirements, it takes lot of time, right? It takes long latency. However, we recognize that there are actually some books which are required by all the EC students. Okay, maybe fundamental of electronics or something like that. So what we do, we create a department library, which is there in our building. I think you people have not come to the campus, probably you're missing. So anyway, so we have a department library. So this department library will have probably only those books which is required for EC students specifically. Those which are very common, they will be placed in the institute library. But from the institute library, we will fetch only those books which are required for the EC students or CSE students. So they will be kept in this library. So that is a department library. Okay. So every department can have its own library, and that department library will have books very specific to the department students. We are fetching the this department library is not probably making its own independent purchase. This is getting all the books only from institute library. But here we have made one more collection. Similarly, we can have both global memory and shared memory. So global memory access takes a lot of time, but we can recognize that threads in a thread block, they are working on a specific problem. Okay, the threads of a thread block, they are working on a specific specific data, specific suppose question or specific problem, or specific algorithm. So all the threads need the same data, right? So that's why if we can keep all the data which is required by the threads in the thread block, then we can keep the data in the shared memory because all the threads in this thread block need that data. Okay, so let me also check the email. Okay, okay. I hope nobody's there in the Teams, right? Have you joined the Teams link?
No, sir.
Okay, I hope nobody's there. Okay, we have almost the full screen. So you understood, right? Shared memory keeps that data which is relevant for the threads in a single thread. A different thread block will have its own shared memory. A different thread block has its own shared memory. So now here is the summary, and I expect you will remember it. I will definitely ask you questions on this in homework or in the exam. So, of course, this is in relation to CUDA, but CUDA is just the programming language. CUDA is the name of the architecture, and CUDA is also the name of the programming language. So, we have registers. Okay, so register is, it is just like, you know, something my own pocket, something which I use very frequently. I keep it in my registers. The computer keeps it in my registers, in its own registers, or something which is very relevant to me, I keep it in my pocket. So int local variable. So when I declare a variable like this, okay, it gets stored in the register. If there is a space in the registers, that means first of all I try to store something in the register, and this variable is local to that thread, so only that thread can see it. When the thread dies, this variable will automatically die. Okay, and because it is stored on chip, registers are always stored on chip. That's why its latency is very small, 1x. But when I declare an array, okay, arrays are never stored in the registers. So here you can see automatic variables without any qualifier reside in register, except that the arrays, per thread arrays, they reside in local memory. Arrays are never stored in the registers, or if there is no space in the registers, then even this can be pushed to local memory, because registers are very small in number. For example, if something I cannot fit in my pocket, I will keep it in my bag, or I will keep it in my bookshelf or in the library. Right? So that's the point. Now, still it is private to the thread, and when the thread dies, these variables will also die. Okay, so lifetime is how long will it survive. So as soon as the thread dies, this array will also die, and because this local memory is in the DRAM, so this is the only this is somewhat counterintuitive thing which you have to memorize. So here, because this local memory is in the DRAM, that's why its latency is very high. Now comes shared memory. So any variable that you decide, that you declare like this will go into shared memory. So as I said, the programmer can write a code to specifically store a data in the shared memory, and this is the code you have to write. Right? You declare a variable as shared, so this variable will always be stored in the shared memory. Okay, so here it will be stored in the shared memory, and as you know, shared memory is visible to all the threads in the block. And whenever the threads in the block die, this shared variable will also die, and its latency is 1x. Why? Because it is on chip. Now comes global variable, and this actually you can ignore because we have not discussed constant memory. And this is just a device. Device means it is a GPU. So this global variable is common to all the threads in the GPU. So this will be stored in the global memory. Its scope is for the entire grid. As long as this application is running, this global memory will be there. When this application is finished, the global memory data will be deallocated, or it will be destroyed or whatever. It will no longer remain valid. It will become invalid. And because global memory is in the DRAM, it is slow. That is 100x. So please ask question if you could not understand it. Anybody has any questions on this? If you have, please feel free to ask.
Please explain shared memory once more.
Yeah. So shared memory is similar to the department library, right? So all the students of this department, only they are allowed to access the department library. Other students of suppose physics, chemistry, they cannot come to our department library. And as you can see here, actually, this our department library is in our same building. So I don't have to cross outside the building. Similarly, shared memory, although it is called a memory, you can see it more as a cache. So shared, first of all, shared memory, it is on chip. As I made this block, this shows whatever is on chip. Okay, so because it is on chip, its access is very, very fast. That's why it is 1x. Okay, latency is 1x because it is on chip. Now, so here all the threads in a block can access the shared memory. As you can see here, this diagram is quite good. So all the threads in this block can access the shared memory. So its scope, that means which threads can see this shared memory? Only the threads in this thread block can see this shared memory. And when all the threads in this block die, that means when their work is finished, that time shared memory is also deallocated. So that's why its lifetime is as long as this thread block is running. Okay, is that fine? Okay, I'll just like to explain this software managed and hardware managed again because I think some students joined late and this concept will come again and again, then you will get confused. So software managed cache is that cache where the programmer can write some code to move the data to this particular cache. That is called a software managed cache. Just like here, we can write, just as here, we can write this variable to be shared, and that's why it will be definitely stored in the shared memory. Whereas hardware managed cache is something where programmer has no control. Whether this data will be stored in the L2, L1 cache, L2 cache, programmer has no control over it. For example, I gave this example like because when you write C++ program or C program or Python program, you never worry what is the cache size of my CPU. You just run it. Hardware itself will worry about which data to move to L1 cache, L2 cache. That is hardware's consideration. It is not programmer's worry. So that's why it's called hardware managed cache because hardware itself is managing that cache. Okay. So as I will show you later, most of the AI accelerators they have software managed cache. Okay, let us just discuss shared memory in some more detail. So parallel programming, yes, please.
Sir, one last point in the second. Yes, sir. Sir, the difference between the local variable and local array here is because the local array is stored in a DRAM, that's why its latency is comparatively higher than the local variable.
Local variable is stored in the registers, and local array is stored in local memory, and local memory is in the DRAM.
Okay, and registers are comparatively on chip placed. Yes.
Yeah, register is on chip. Yeah.
Thank you, sir.
Okay, so now let us discuss shared memory in somewhat more detail, just a little bit more detail. So parallel programming is not easy. Suppose you want these puppies to eat their food in parallel, and this is, as I said, just theory. So can anybody tell what will happen in practice?
Chaos, sir.
Chaos. Yes, you are a practical man. Oops. You are a practical man. They will not eat their own food. They will eat each other's food, right? So don't rely on something practical. So similarly, when we expect our threads to work in parallel, actually they will not. It's not so easy. They will take each other's. They will take each other's data. So now let us, we are talking about shared memory. So any department library, if you're operating, it needs some kind of synchronization. But when it will be successful, when students have similar choices. For example, suppose in autumn month. Suppose in autumn month, if our department starts offering 1,000 courses, then students will need thousands of books, 1,000 books, right? So now our department library cannot hold so many books. But if we offer only 10 courses, okay, if we offer only 10 courses, then probably students will need only 10 books. So then at least our department library can work finally properly because it needs only 10 books. So that can be managed. So when students have similar choices at similar point of time, for example, this student also needs network hook, this also needs networks, algorithms, compilers. So then at least it is manageable. But when one student needs data mining, other needs algorithm, one student needs algorithm compilers, compiler network, then which book should I keep in the department library? That becomes difficult, assuming my department library is very, very small or limited in size. Similarly, in shared memory also, uh, in shared memory also, uh, when when threads need the threads need the same piece of data at same point of time, then you can bring that data to the shared memory. But if they need different data, then which data to bring to the shared memory, that is not very clear. Then shared memory will not be effective. Okay. So now, to actually avoid this problem which I mentioned here, right, we need some kind of discipline. Okay, we need some kind of synchronization. So that is called barrier synchronization. So this is a function called sync thread. It's just a function. So all threads in the same block must reach sync threads before any thread can move on. Okay. So I will skip this part. So here, this is the idea. Suppose you have so many threads. All right. Now, uh, some of the threads may be running slow. Some of them may be running fast. So here we put a barrier that although this thread n minus 2 has come here very quickly, but only when other threads reach here, right, only when other threads reach here, only then all the threads can make the progress. So this thread will have lot of, I mean, because this thread has come very early, it has to wait very long time. Okay. Although this thread was originally fast, but because we put barrier synchronization, this thread will have to wait. Whereas, suppose this is the slowest thread, only when this thread reaches here, then other threads can also make progress. So it's just like example of suppose deadline. Suppose I keep the deadline that okay, that only when all the students submit homework 1, I will start teaching. Okay, I will not teach you unless all of you submit homework 1. Okay, so now what happens? Suppose the deadline was 31st August. So somebody submitted their homework on just 5th August. Somebody submits on 10th August, 15th August, 25th August. Somebody submits it, 1 minute before the deadline, 11:59 p.m., which is what usually happens. And then students say that the laptop got slow, Wi-Fi problem, this. So sometimes it happens 5 minutes after 12. So now somebody who submitted their homework on 5th August, they have to wait for 26 days. Right? They have to wait for 26 days. Whereas somebody who submitted only 1 minute before, they lose only 1 minute. Probably they were running slow. Okay, so that's the idea of barrier synchronization. So at least for the next class, that means in the September, all of them are at the same point. So there is at least some discipline. It's not that I have started teaching the next component and some students have not even covered up. Okay, so this is just to give you a rough idea uh, in a joking manner. But idea is sometimes you allow the threads to work in parallel, but at some point you do want that, okay, all threads should be available to do this. Okay, so everybody understood the idea of barrier synchronization? Or do you have any questions? Any questions here on barrier synchronization or the previous topic? Okay, very good. So here there are some references if you want to.
Okay, sir.
Yes, please.
Sir, in the last slide, sir, like we are
Here.
facing this. No, sir, the next slide.
Mhm.
So here we are like assuming that all the threads will be accessed. Like,
All the threads will run. Yeah, yeah.
uh,
Suppose one thread does not run, then you are stuck.
yeah, sir. So like in that case, like no data will be accessed to the memory, right?
Yeah, then it will be called a deadlock.
Okay. Okay.
Then the programmer has to come and debug it.
Thank you.
Fine.